Hello, my name is Dana Jenkins. Along with my team members Emily Enos, Tommy Travis, and Lily Zhang, we are going to discuss our research project for Kennesaw State University's IT7113 data visualization. Our project is research visualizing the discrimination abilities of binary classifiers. This is the agenda for our report. I'm going to discuss the problem statement and research questions and go into the literature review process. The rest of the report will be discussed by the other members of our team. As research for our project, we looked at a number of different topics. We had a member of our team who was very interested in the healthcare field, so we were looking at disease prevention, disease prediction for benign versus malignant. That ends up being a binary classification problem. And that binary classification problem is used in many areas, whether it's in benign versus malignant, or in a pass-fail system for a factory, or even email with your determination of spam versus not spam. The other thing we do realize is that effective visual evaluations on the performance of those binary classifiers is very important. Our objective is to review and compare visualization plots of binary classifiers, and doing this using different types of software and compare their features. We know that some programs are easier to use in certain types of plots, and other programs are easier to use in other different types of plots. And we want to make sure that when you're visualizing data, that the data looks is usable with whatever program you're actually using. We're going to go through this in looking at two different comparison principles. Our first principle is how a strong plot can show the difference between binary classifiers correctly classifying true positive and true negative. And second principle is how easily a plot can be interpreted and understood by people who may not have a statistical background. Now, the term easily is a subjective term, but we want to find a process that we can show someone who may have a high school education that has had maybe geometry or trigonometry in their course of study, and try and stay away from heavy statistical information. This last topic is on the literature review. We have reviewed a number of different articles. We have cited some of those articles in this report, and you'll find those in our references section of this report. And we have a number of other items we researched that we use as background information, but did not cite that information. It's a good reading list for if you want to delve more deeply into these topics, and you'll find those in our resources section of our report.
Hello, this is Lily. I will talk about the data, some basics of visual evaluation plots, and also the plots from two statistical models. The data used in this project is the breast cancer data from UCR Machine Learning Repository. It includes 699 observations with one ID variable called sample code number. It also includes 9 independent variables which are used as the features in the modeling, as well as one binary dependent variable called class. It labels each observation as either benign coded as 0 or malignant coded as 1. This is the target we expect to predict in the modeling. We want to visualize the performance of logistic regression and naive Bayes. On this dataset, they will train on the training data and then perform the predictions on the test data. Each model estimates the probability for an observation being malignant. For example, for the sample in the first row, its class value is 0, indicating it's benign. Logistic regression estimates the probability for being malignant is 0.3422. Naive Bayes estimates its probability for being malignant is 0.4669. So how can we evaluate these estimated probabilities based on true outcomes as indicated by class here? This is where visual evaluation plots in this research come in. Let's first review two key basic terms used in visual evaluation plots. One is probability threshold or cutoff, the other is confusion matrix. A probability threshold or cutoff determines binary outcome from estimated probabilities. The ones with estimated probabilities above the threshold are classified as malignant or 1, and the others are classified as benign or 0. For the examples in Figure 2, if we use the threshold 0.33, the first three rows would be classified as malignant or 1. The last two rows would be classified as benign or 0, as shown here by the column predicted. As shown earlier, some predictions are correct while the others are wrong, so we use confusion matrix to quantify the difference between true values and predicted results, specifically true positive, false negative, and true negative. Some examples are highlighted here. For example, the row highlighted in blue is true positive. Based on the confusion matrix, we can compute the true positive rate or sensitivity, true negative rate or specificity, false positive rate and accuracy. For example, in Figure 5 earlier, the true positive rate is 1 above 2. Apparently, if we use different probability thresholds, we will get different values in the confusion matrix like true positive rates and true negative rates. Many evaluation plots like RC curve are drawn based on varied probability thresholds. In the next section, we will show 4 visual evaluation plots, including RC curve, density plot, positive indices per decile, and accuracy. RC curve presents a visual summary of trade-offs between false positive rates and true positive rates at varied possible probability thresholds. Its x values are false positive rates, and its y values are true positive rates. Some people also show area under the curve and 95% confidence interval in the plot. A good model is the model with high true positive rate when false positive rate is low. This is reflected in ROC curve as the line is shifted towards the upper left corner. Just as shown here, the ROC curve of naive base on the right is shifted towards the upper left corner much more than the logistic regression on the left, so naive base differentiates the malignant and benign cases better than logistic regression. My team member Tommy will talk more about ROC curves.
Hi, my name is Tommy Travis, and I will be for this portion of the presentation, I will be analyzing rock curve charts, and they were created using the Microsoft Excel charts tool. We found that creating rock curve charts using Microsoft Excel to be quite adequate, and it yielded some interesting results. Some may find Microsoft Excel charts to be customization and of standard format and combinations of different data sets and different data type graphs to be awkward and not natural. However, that's not the case here. Each binary classification is analyzed to the probability of benign or malignant diagnosis. The data was first converted from the raw data via a pivot table. And from that pivot table, we used the data to calculate sensitivity. And from that sensitivity, we got our X and Y coordinates, and the rock chart was created from that information. Each chart has an inflection point that is depicted or visualized by a red dot, and it marks the dividing line between true positive and everything after that being false positive. The next several slides reflect an area under the curve, or AUC, of less than 90%, which means that the results are less accurate. In this visualization, we analyze the clump thickness. When correlated to the data, any tumor with a clump thickness equal to or greater than 5, it has a higher probability of being malignant. In this next visualization, we analyze marginal adhesion. When correlated to the data, any tumor with a marginal adhesion classification equal to or greater than 3, it has a higher probability of being malignant. In this next visualization, we analyze normal nuclei. When correlated to the data, any tumor with a normal nuclei classification equal to or greater than 3 has a higher probability of being malignant. In this next visualization, we analyze mitosis. When correlated to the data, any tumor with a mitosis classification equal to or greater than 2 has a higher probability of being malignant. As you can see, this next slide has a different area AUC, as you will see in the next 5 slides. The area under the curve is quite filled out, and as we analyze uniformity of cell size, when it's correlated to the data, any uniformity of cell size classification equal to or greater than 3 has a higher probability of being malignant. In this next visualization, we analyze bare nuclei. When correlated to the data, any tumor with a bare nuclei classification equal to or greater than 3 has a higher probability of being malignant. As you can also see, it still has an area under the curve of about 90% of the chart. In this next chart, we analyze single epithelial cell size. When correlated to the data, any tumor with a single epithelial cell size classification equal to or greater than 3 has a higher probability of being malignant. As you can see, it also has an area under the curve of about 90%. This visualization analyzes uniformity of cell shape. When correlated to the data, any tumor with the uniformity of cell shape classification equal to or greater than 4 has a higher probability of being malignant. And it also too has an area under the curve of more than 90%. And in this visualization, we analyze bland chromatin. When correlated to the data, any tumor with a bland chromatin classification equal to or greater than 4, it has a higher probability of being malignant. And you also too see this is again an area under the curve of about 90%. The last 5 binary classification rock charts all have an area under the curve of about 90%. You may have noticed that the inflection points of those 5 rock charts also plotted in the same area of the chart. So the next slide is a combination of the last 5 binary classifications plotted onto one chart, investigating for the possible correlation of data. And as you can see on this chart, we analyze 5 binary classifications, and the inflection points are encircled with this blue rectangle, blue rounded rectangle, and you can see that those inflection points are all within the same tight area. So that means when correlated to the data, any tumor with the 5 binary classifications equal to or greater than 4 has a higher probability of being malignant. Thank you so much. This is Tommy Travis, and this concludes my portion of this report. My teammate will go further with more information.
Next, I will talk about density plot. It provides a visual information on the scaleness and distribution of estimated probabilities for each class. X values are probability thresholds and Y values are the density. It is colored by class 1 and class 0 separately. A good model has lower estimated probabilities for class 0 and higher estimated probabilities for class 1. This is reflected in the density plot as the distribution of estimated probabilities for class 0 is shifted towards 0, while the distribution for class 1 is shifted towards 1. As shown here, the distribution of estimated probabilities for class 0 is colored in pink, and the one for class 1 is colored in green. For logistic regression, they pretty overlay together. For naive Bayes, the green one is shifted towards 1 much more than the pink one, so naive Bayes is much better than logistic regression here. The plot of positive instances per densa visualizes the number of positive instances in each densa. X values are the densa or 10 buckets of estimated probabilities ranked from highest to lowest. Y values are the number of positive instances. A good model has higher estimated probabilities for class 1. This is reflected in this plot as the number of positive instances is high when X value is low and decreases sharply as X value increases. As shown here, for naive Bayes, the number of positive instances in the first densa is much more than the others. For logistic regression, the difference is not very obvious. The accuracy plot here presents a visual summary of accuracy at different probability thresholds. X values are probability thresholds and Y values are the accuracy. For balanced data, a good model is definitely the one with the highest accuracy. But for unbalanced data, a model with high accuracy is not necessarily a practical useful model. We need to check other measures like RC curve. It is easy to see the model that produces the highest accuracy, 93%, is the naive model with the threshold 0.3. Next, my team member Emily will talk about the modeling and plotting with SAS Enterprise Miner.
Hi, this is Emily Ennis. We determined that using SAS Enterprise Miner is another valid way of creating models regarding cancer diagnoses using this breast cancer data set from Wisconsin. During data exploration, it was determined that 16 records had invalid or missing data. Those records were removed, leaving us 683 observations, 11 variables, and 0 missing values. Normally, it would not be necessary to delete records if you're just using decision trees. Decision trees are able to handle missing values. But in this case, I'm also going to create regression models, which does require full records and no missing data or invalid data. I also created data partitions, 70% for training and 30% for validation. The first model that was created was a simple regression model. The data that returned for validation was the average squared error of 0.039 and a misclassification rate of 0.049. Also, there is an image of the cumulative lift on the appendix page A3, which shows the training and validation align after a significant number of records have been read in. The next item was the stepwise regression model. It iterates through all of the possible indicators within the file of a person being diagnosed with breast cancer. The stepwise selection said that the uniformity of cell size, bare nuclei, clump thickness, uniformity of cell shapes, all were the primary indicators of a person being diagnosed with breast cancer. The average squared error for this file again was 0.039 and 0.049. Creating the regression models is effective, but comparing those to the decision tree models makes it even more effective. Now, I did a default decision tree, which is just whatever's on the default of Enterprise Miner, it'll go ahead and create a decision tree from that. Based on this, the initial split was for the uniformity of cell size, and the next split was bare nuclei. So it determined that these two items were significant in determining if a person will be diagnosed with breast cancer. The average square error was a 0.042, and 0.044. The next step was to create a maximum tree, so I increased the number of levels the tree could create. This tree also determined that the uniformity of cell size and bare nuclei were the most valid indicators of a person being diagnosed with breast cancer. Although the average square error seems to be on the rise, we have 0.059. Also, the misclassification rate has increased to a 0.63. At this point, I thought it would be beneficial to manually manipulate the tree. So in this case, I wanted to create a three-way tree, which it will only split 3 ways instead of just 2. Before, it was just looking at 2 different possibilities on the first level. So now we have the uniformity of cell size, bare nuclei, clump thickness, and normal nuclei, I'm sorry about the pronunciation, as options to determine if someone will be diagnosed with breast cancer. The statistics on the validation data has an average squared error of 0.043. The misclassification rate is a 0.048. It's looking a little better, but not quite what I think I would want to see. So I'm going to continue. This tree focuses on the average squared error. Now that I'm seeing the similar results from the other models, it's a good indicator to me that this is the best at this time that we're going to do with these models. With comparing all the models to one another, as will be displayed on Appendix A11 through A12, the model selected was the average squared tree. It seems to present the most positive data regarding the determination of a person being diagnosed with breast cancer. I really believe that the training data yielded better than the validation data. So I would continue on with this and maybe create a 50-50 split of the data. Since there's only 683 records, it's really not enough to get a good determination. So if we can accumulate more data, it will be helpful in this model. And then I will continue to run these and additional models to make a final determination.
By comparing the model evaluation plots on the breast cancer data in this project, we have the following conclusions. First, accuracy plot and density plot require less statistical background to understand, compared with LC and positive instances per densa. Second, density plot is better at showing how well a model differentiates each class, compared with accuracy plot. Third, RC curve provides the most precise measure of the model performance compared with others, although it is the hardest one to understand. Fourth, positive instances per densa directly shows a model's discrimination ability on the positive class, although it requires moderate efforts to understand. So back to the comparison principles we set up at the beginning, based on the first one, which is about how strong a plot shows the performance of models. We see that LC curve is the best one, followed by positive instances per densa, density plot, and accuracy. Based on the second one, which is about how easily a plot can be understood and interpreted by average people, we see that the accuracy is the best one, followed by density plot, positive instances per densa, and LC curve. This is a list of references and the resources we have referred to in this project. And here are some information included in appendix.